In the graph shown above, the y values are rising, meaning we're moving uphill here from negative infinity until we get to -2. They are rising again from 1 to infinity. They are falling between -2 and 1. When the y values are rising, we say that the function is increasing. And when they are falling, we say that the function is decreasing. Let's look at the areas where the function is increasing. If you look at these areas and you were to draw tangent lines to the function, you can see that these tangent lines would all have positive slope. Likewise, if you look at the area where the function is decreasing and look at tangent lines along that area, you can see that they would have negative slope. A couple of definitions before we move forward. Critical values are any value in the domain of f where f prime, the derivative, equals 0, or where the derivative does not exist. Critical points are the points that correspond to the critical values. For our first example, we are going to find all the critical values, and the function we are doing this for is f of x equals x cubed plus 3x squared minus 9x plus 4. Think back to what the definition said. Critical values are places in the domain of the function where the derivative equals 0 or where the derivative does not exist. This function is a polynomial function, and so it is continuous everywhere. We don't have to worry about where the derivative might not exist, but we do need to know where the derivative equals 0. So the first thing we're going to need to do then is find the derivative. So f prime equals 3x squared plus 6x minus 9. To find the critical values, we set the derivative equal to 0. And when you look at this derivative, notice that each term can be divided by 3. So I'm going to factor out a 3. That will leave us with x squared plus 2x minus 3. Now let's continue factoring. What does this factor into? This factors into plus 3 and minus 1. So our critical values, or critical numbers, whichever one you want to call them, are x equals -3 and x equals 1. It didn't ask us to do this, but if it wanted you to find the critical points, then you put those values back in for x. So the first critical point will be at -3, and putting -3 back into the original will give us, let's do this down below here, -27 plus 27 plus 27 plus 4. So these two have wiped each other out, so 31 would be your y value. At the x value of 1, if you put 1 into the original, you will have 1 plus 3 minus 9 plus 4, which will give you -1. On our second example, we have a rational function, and we want to find the critical numbers for this rational function. A little trick that will help you find this derivative is to rewrite this as 5 times the quantity of x minus 1 to the -1. I'm rewriting it so that I can use the chain rule instead of the quotient rule. You can use the quotient rule. There's nothing wrong with that. The chain rule is just a little bit faster. So the first thing we have to do then to find our derivative is drop the -1 times the 5, which gives us -5. Leave the inside the same. Go down by 1, so our new power is -2. And then take it times derivative of the inside, which is 1. So now I'm going to rewrite this back in fraction form. -5 times 1 just gives me -5, and then I'm going to move the quantity back to the denominator and give it a positive exponent. This version is what I want to look at when I am finding my critical values. Remember that critical values happen where the derivative equals 0 or where the derivative does not exist. This derivative, because it's a fraction, can only equal 0 if the numerator equals 0. So let's just write that down to help you remember. Fractions equal 0 if the numerator equals 0. This numerator is the constant of -5. The only way for the numerator to be able to equal 0 is if there was a variable there. So f prime cannot equal 0 because there's no variable in the numerator. But remember that we said the other place where critical values happen is where the derivative does not exist. When you have a fraction, the fraction does not exist when the denominator equals 0. So let's, again, as a reminder, fractions do not exist if denominator equals 0. Our derivative would have a 0 in the denominator at x equals 1. So our critical value is x equals 1 because f prime does not exist at x equals 1. That's our only critical value for this question. Two more definitions. A relative maximum is the point at which a graph changes from rising to falling. Think about this. If you are going uphill and then you stop and start going downhill, there's your maximum, your peak. A relative minimum is where you change from falling to rising. So again, think about it. If you're falling and then you stop and you start rising, there is your minimum. If you look at this given graph, the relative maxima occur at the x values of -3 and 2, and the relative minima occur at the x values of -1 and 4. Maxima and minima are the plurals for maximum and minimum, just so you're aware of that wording. To find your local extrema, which means finding your maximum or minimum, you are going to find any x values at which the derivative changes sign. A horizontal point of inflection, which we abbreviate with HPI, is a critical value at which the derivative does not change sign. So it's going to be a place where the derivative equals 0, but it doesn't change from increasing to decreasing or vice versa. The first derivative test is used to find extrema, to find a max or a min. The first derivative test says let C be a critical value. If f prime, the derivative, is positive to the left of c and negative to the right of c, then c is a local max. If the derivative is negative to the left of c and positive to the right of c, then c is a local min. If the derivative is the same sign on both sides of c, then it is neither a max or a min, it is an HPI. In example 2, we have a lot of things that we're going to be doing. First, we're going to find the derivative. Then we're going to find the critical values and the critical points. Once we have those, we're going to find where the function is increasing or decreasing and any local extrema or HPI. Then we're going to sketch a graph. Our first example for which we're going to do all these things is f of x is 2/3 x to the third minus x squared minus 24x minus 4. First thing we want to do is find the derivative. So our derivative, if we drop 3 and take it times 2/3, we're going to get 2x squared minus 2x minus 24. Now remember that what we're going to do is take this derivative, set it equal to 0, and then factor it if we can. Each of those items divides by 2, so I'm going to pull out a 2 first and have x squared minus x minus 12. And then that will factor into x plus 3 times x minus 4. So my critical values are x equals -3 and x equals 4. So my critical points, I'm going to take those numbers and put them into the original function. If I put -3 into the original function, I get 41. If I put 4 into the original function, I get -73 and 1/3. Once you know those numbers, what you are going to do is take those critical values and put them on a number line in order. So here's -3. We don't need anything but the critical values. So these are the x values we're talking about. And what we're going to look at is what happens in the derivative. At -3 and +4, our derivative equaled 0. What you do with this then is you test numbers from each of the sections that your number line is divided into. We are now divided into 3 sections. So we are going to test in the derivative numbers from each section. I'm going to pick a number on the left of -3. The easiest one to do would be -4. Put -4 into the derivative. You could put it in any version that you want to. I find it easiest to put it in the factored version. I would get 2 times -1 times -8. All I care about here is what sign would I get. If I did that multiplying, I would get a positive. So what that means is that any number that I put in on the left side of -3 will give me a positive answer. Now pick something between -3 and +4. The easiest thing is 0. Put 0 into that derivative. You would have 2 times 3 times negative 4. Again, remember, all we care about is what sign do we get. We don't care what the number is, just what sign is it. That would give us a negative answer. So every number between negative 3 and positive 4 would give us negative answers. Now go to something to the right of 4. Again, the easiest one would be 5. Put 5 into your derivative, you would have 2 times 8 times 1, which will be positive. So every number to the right of 4 would give you a positive. This that we have done is called a sign chart. And what it tells you is where the function is increasing or decreasing. Anywhere that your sign chart is positive, your function is increasing. And anywhere that it's negative, your function is decreasing. So when the directions tell us to find where the function is increasing or decreasing, we write that using interval notation. And your number line has the interval notation right there on it. We are decreasing between negative 3 and 4. Everything from negative 3 to 4 is decreasing. We always put parentheses around these because the place at exactly negative 3 or exactly positive 4 is where we equaled 0. So we're not decreasing there. We are increasing from negative infinity to negative 3, and again from 4 to infinity. That U stands for union, and we typically use that U when you need to write more than one interval. So now we know where we are increasing and decreasing. So what that tells me then, because I was increasing before negative 3 and decreasing after negative 3, that tells me that that point that we found of negative 341 is a relative max. And then because we are decreasing before and increasing after the positive 4, that tells me that positive 4 is a relative min. The point where that happens was 4 and negative 73 and 1/3. Now we need to sketch a graph for this function. This is going to be a rough picture. We don't have a ton of information. We have 2 points and we know where it's increasing or decreasing. So looking at those points, notice that my y values are 40 and 70, so I can't count by ones on the y-axis. I'm going to count by tens. So this would be 20, this would be 40, here would be 60, here would be 80. Down below we'd be negative 20, negative 40, negative 60, negative 80. And then on the x-axis, I am going to count by ones. So here's 1, 2, 3, 4, 5. So let's put our points into place. At negative 3, 1, 2, 3, we're at 41. This just needs to be an estimate. It doesn't need to be perfect. This is a sketch. At positive 4, we're at negative 73. So we're down in here. Now think about what we said. We were increasing from negative infinity to negative 3. So we're moving upwards until we get to negative 3. Then we are decreasing until we get down to positive 4, and then we start increasing again. When these are polynomial functions, that peak and valley should be a nice smooth turn. It shouldn't be a sharp point. Do the best you can. They don't have to be perfect. They are just sketches. And this would be the sketch of the graph of the original function that we had. For our second example, our function is x cubed plus 3x squared minus 9x plus 3. The first thing we want to do is find the derivative. Our derivative will be 3x squared plus 6x minus 9. Set that derivative equal to 0. We're going to factor out a 3. That will leave us with x squared plus 2x minus 3. And then that factors into x plus 3 times x minus 1. So my critical numbers are x equals negative 3 and x equals 1. Now, to find the critical points, remember we put those values in the original function. If we put in negative 3, we get the y value of 30. And if we put in 1, we get the y value of negative 2. Just a reminder, put into F to find those y values. Now that we know our critical values and our critical points, we're going to set up a number line with those critical values on it of negative 3 and 1. These are the x values, and this is where our derivative equaled 0. Now we're going to test a number from each region in the derivative. I'm going to test negative 4. If I do that, I will have 3 times negative 1 times negative 5. What sign do I get from that? A positive. So every number on the left side of negative 3 will give you a positive answer. I'm going to test 0 for the middle section. If I put 0 into my derivative, I will get 3 times negative 1, which will give me a negative. So all of these numbers will be negative. Then I'm going to test 2 because it's on the right side of 1. That will give me 3 times 5 times 1, which is a positive. So all of these answers would be positive. What we know now, because of that sign chart, is that our function is increasing from negative infinity to negative 3, and again from 1 to infinity, and that it is decreasing from negative 3 to 1. Now, because I went from increasing to decreasing at negative 3, that means that I have a relative max at negative 330. And because I went from decreasing to increasing, I have a relative min at 1, negative 2. Just like on our last example, I've got a big Y value. So I'm going to count by fives this time, which means my second mark would be 10. The fourth mark would be 20, and the sixth mark would be 30. And my X values, I'm going to count by ones. When you use a different scale, please mark it so that I can tell what you have done. So looking at this then, we have a relative max at -3, 1, 2, 3, up 30. And we have a relative min at +1, -2, so it's going to be in here. We know we are increasing until we get to -3. We decrease from 3 to 1, and then we increase again after 1. So there's a sketch of that original function.